Now I'm continuing with the drawings of the Fourier series coefficients and the sine waves. You see here I have a DC amount, and I'm adding, this is DC, and I'm adding the first sine component and third sine component. B1 is the 2 over pi, and I'm adding 1 over 2 plus 2 over pi sine 2 pi over t, okay? And I'm adding 2 over pi times 3. You see, this is n times sine 2 pi 3 over t. Okay, so I have added a 0. This is the first fundamental frequency, okay? And this is B1, and this is B3, and then third harmonic. So if we do this like that, we will see, for example, A0, B1, B3, B4, 5, 7, 9, and 11. If I add all of these, I'm going to get this kind of a signal. Okay, this is a signal. You see, it looks very much like the original one, with some ripples, with some something like that. Okay, it's called ripples. And if I increase this even more, then I will get even more closer to our pulse like this one. Okay, so because there is a very fast change here arkadaşlar, very fast change means high frequency. Okay, fast change means high frequency. That's why we have even higher frequency components in my pulse signal like that. Okay, so this is very critical that you understand that if I add many signs here for this kind of pulse signal with a certain DC component and some sine waves with different coefficients. You see the coefficients are 2 over pi, 2 over 3 pi, 2 over 5 pi, 2 over 7 pi. The coefficients are decreasing as we go further with n, but they still have some contributions to the final signal. Okay, so I would like you to understand this part like that. If you remember, we talked about our original signal f of t, and we had A's and B's. Now I included A0 in my formulations because it was like A0 plus m from 1 to infinity am times cosine something plus from n from 1 to infinity bn sine okay? So if I include this here, if you think about cosine 2 pi times 0t over t, it is like cosine 0. So cosine 0 is equal to 1, right? So if I add it here, nothing will be changed. So I can say am cosine 2 pi m t over t, and from 0 to infinity. So this will be my coefficients, okay? Now I'm going to start talking about one thing here. Sorry, I'm going to change. I'm going to say, now I have a new thing to present you. If you remember, e to the j omega 0 t is equal to cosine omega 0 t plus j sine omega 0 t, right? So this was a kind of complex exponential representation of cosine and sine. You see, we have cosine and sine here, and we have the coefficients of cosines and sines. Instead of dealing with this cosines and sines, Fourier have come up with that idea of representing everything in terms of complex coefficients, okay? Cn e to the power j 2 pi n t over t. So everything, every kind of signal, whether it is a real signal or a complex signal, you can come up with this Fourier series representation. Okay, we will always use this kind of a representation from now on. We will not use cosine and sine like that, but instead we will be using this formulation in our analysis. So this is Cn, and Cn is like AM plus JBN. Okay, so it's a complex signal. The real part of my complex signal will be the coefficients corresponding to cosine, okay, and imaginary part of my coefficients will be the coefficients related to sine, okay. So this is very important. We are not going to be dealing with ANs and BNs, but we are going to be dealing with CNs. It's also true for MATLAB. You will get, using FFT function, you're going to get complex coefficients. And those coefficients, the real part of that coefficient will be related to cosine, and imaginary part of that coefficient will be related to sine, okay? How much my signal is similar to cosine will be reflected in the real part of my coefficient. How much similar of my signal to the sine wave will be represented in imaginary part of my coefficient. So I will have, let's say, 0.1 plus j 0.2. That means this is my AM for certain, let's say A1, and this is B1, and this is going to be C1. If I see C1 as 0.1 plus j 0.2, that means my signal at the fundamental frequency is similar to the original signal with a 0.1, let's say, coefficient 0.1 similarity. Okay, and then this will be like 0.2. It is going to be similar to sine wave. Okay, so, and this is my, I'm adding up CNs, Cn times e to the power j omega n's with, to obtain f of t. Okay, so this is like composing our signal using sines and cosines. This is like composing my signal, okay, using complex exponentials. Okay, I'm adding up complex exponentials like sines and cosines together, multiply them with certain coefficients related to how much of that component is similar to the original signal, and then we will obtain f of t by adding up those signals, which is called synthesis equation. Okay, synthesis equation. That means I'm synthesizing my signal using sines and cosines or complex exponentials. Here, the formulation is like that. Cn is equal to 1 over t from 0 to t, or I will go over one period, and f of t, again, you see it's a kind of similarity formulation, minus j 2 pi n t over t dt. Okay, so this is my signal, which I would like to find out the coefficients of. So now I'm trying to analyze my signal, analysis equation, okay? What does analyze mean? For example, blood analysis. What does blood analysis do? I can find out how much white blood cell, red blood cell exist in my blood. It's an analysis, it's a decomposition. I'm trying to find out for each harmonic, like how many sines I have, how many cosines I have in my signal to represent my signal. Okay, this is the analysis equation. So I'm going to use this synthesis equation and analysis equation from now on in many different applications. Okay. So if you come here and try to do the same thing, arkadaşlar, the formulation, our signal was like that, t over 2. I'm doing the same signal. I'm only focusing on one period. And then this is how I do it. Cn is equal to 1 over t from 0 to t over 2 times 1 times e to the power minus j 2 pi and t over t dt. Okay. So I wrote my signal. In this part is 1, the other part is 0. So I say from 0 to t over 2, and this part is like that. And then I'm putting this as it is. And then finally I will write, you see, e to the power ax dx. If I take the integral, how do I do it? This a goes down, 1 over a, e to the power ax from, let's say, b to c, from b to c, okay? So that was our integration property. So I will take this one as my a here, so I will reverse it. Cn is going to be equal to 1 over t times t over minus j 2 pi n. Okay, I just reversed this part. And then e to the power minus j 2 pi and t over t from 0 to t over 2. So t's will go away, and I will have 1 over minus j 2 pi n times e to the power minus j 2 pi n over t times t over 2 minus e to the power 0, right? I put 0 instead of t. So this is 1. This is t's will go away, 2's will go away, and finally I will have 1 over j 2 pi n. This minus will change this one into plus and this one into minus, so it will be 1 minus e to the power minus j pi n. Okay, this is Cn. So what is this part? E to the power j pi n. For example, for n equals 1, it is 1 over j 2 pi times 1 minus e to the power minus j pi. What is e to the power j pi? It is here, right? So this is the cosine, this is the sine. So this is the imaginary part, this is the real part. So it will be a real one, and it is minus 1. So this will be minus 1. And finally, it will be 1 minus minus 1, 2 over j 2 pi. And 2's will go away, 1 over j pi. Okay? So Cn will be 1 over j pi. How about C2? We will say 2 over j 2 pi times 2 times 1 minus e to the power j 2 pi. What is e to the power minus 2 j pi? It is here, okay? 2 pi. It's going one cycle like that, and it is 1. So 1 minus 1 is going to be equal to 0. So all even CNs, C even integer, it will be 0. For odd integers, it will be like Cn. For odd ends, it will be 1 over j pi n. Okay, so if you see that 1 over j or I pi n for n's equal to plus and minus 1, and these are odd integers, either negative or positive, and these are even ones, and for the even ones, Cn's are equal to 0. For the odd ones, Cn's are equal to 1 over j pi n. Okay, so if you look at this, we will see that Cn's can be found as a complex number like that. If you look at the complex number j pi n, it becomes like, if you multiply it with j over minus j over pi n, right? J square is minus 1, or I square is minus 1. In physics, we use I, okay, for complex variable, let's say I. But in electricity, in electrical engineering, we use J because I is already used for current, okay, or current, the current, akım. So J is not used. That's why we use, I is not used, so we use J instead of that one, okay? So what do you see here? It's like, if you Cn is equal to An plus Bn, let's say JBn, and Bn's are like the coefficient, like it is related to sign, okay? Because it's like a purely imaginary coefficient. So if it is purely imaginary, that means it's only sine signals. If it were only purely real, then it would be a cosine signal. If it is like 1 plus j something, then it is both sine and cosine that exist in the signal. Okay, so for now, that's the end of this part.